In chapter 23, we're going to talk about electromagnetic waves, henceforth known as just EM. Save us some time writing. Static charges have static electric fields. Bar magnets have stationary or constant magnetic fields. But when electric fields are time varying, they vary with time, they produce a time varying magnetic field. Nature loves symmetry. We also get the exact opposite. When a magnetic field is time varying, it produces a time varying electric field. The result of this interaction are electromagnetic waves. Now, 1865, James Maxwell summarized pretty much everything we know about electromagnetic waves with his 4 Maxwell's equations. These include Faraday's law, Gauss's law, Ampere's law, and another form of Ampere's law, one having to do with electric fields, one with magnetic. The laws are difficult mathematically, but we do know that one of the things that they led to was the idea that light was an electromagnetic wave. And when they discovered that light travels at sea and electromagnetic waves travel at sea, they knew that Maxwell had gotten it right. There's basically 4 important characteristics we want to talk about. And I'm going to elaborate this. 4 important characteristics of electromagnetic waves in a vacuum. Number 1, electromagnetic waves are transverse waves. The electric field is perpendicular to the magnetic field, and both are perpendicular to the velocity. What does that mean? That means that if you have a situation where the velocity is in the x direction and the magnetic field, or let's say the electric field, is in the y direction, the magnetic field will be in the z direction. Draw a picture of what that electromagnetic wave might look like. See if we can stay reasonably straight. I draw my electric field in blue. It's a sinusoidal wave oscillating up and down, looks like a sine wave. Not perfect, but you get the gist. There's its maximum value and it's oscillating up and down like this. Straight up, straight down. If the magnetic field, this is oscillating, this is the x-axis, it's oscillating in the xy plane. The magnetic field is also oscillating, and it has its maximum value at the same time that E has its maximum value. But it's oscillating, this is harder to draw, but it's oscillating more or less, well, not more or less, it's oscillating in the XZ plane. So if I were to draw vectors for it, they are pointing parallel to the z-axis back and forth. It's not a beautiful picture, but hopefully you get the idea. There is a right-hand rule for determining this relationship from E to B. Right-hand rule. You put the thumb of your right hand in the direction of the velocity, and then the fingers will curl from E to B. Notice if you look at the picture, you hold up your right hand, you put your thumb in the point of X. When E points up, the fingers curl towards the positive z-axis. But when E points down, your fingers curl to the negative z-axis. So when E points along the negative y, B points along the negative z. So that's one of our properties. Property number 2. There's a fixed ratio between the electric field size and the magnetic field size. That ratio of E to B, if we're just looking at their magnitudes, is C, the speed of light. C is the speed of light and C is equal to 3.00 times 10 to the 8th meters per second. Important thing to realize is although the numerical size of E is always much larger than the size of B, if the magnetic field is 1 Tesla, then the electric field is going to be 3 times 10 to the 8th volts per meter. That doesn't really mean the electric field is stronger than the magnetic field, because electric fields and magnetic fields have completely different units. It's like comparing the number of pounds to the number of miles. $27,000 pounds is not necessarily bigger than 15 miles. They just don't compare. They're not the same thing. The third property is that electromagnetic waves travel with a definite, constant speed. They don't speed up and slow down when they're traveling through a vacuum. We call that speed c. And according to Maxwell's equations, c must be equal to 1 over the square root of epsilon naught mu naught. That is vacuum permittivity times vacuum permeability. And it equals 3 times 10 to the 8th meters per second, or about 186,000 miles per hour. Now, light can slow down, but it will never travel faster than c. c is the fastest possible speed for anything in the universe. When light does travel through other mediums like glass and water, it does actually slow down. And the fourth characteristic is that electromagnetic waves do not require a medium. When a sound wave travels through the air, it requires the air. It's actually air molecules that are oscillating. But in an electromagnetic field, the thing that oscillates are the electric fields and the magnetic fields. And it's that oscillation that makes them a self-propagating wave. I'm going to do a lot of different examples. Let's just think of an example to do. How long does it take an electromagnetic wave to travel to the moon? One example of electromagnetic waves are radio waves. Now, radio waves are like light. They're electromagnetic. They are not like sound, which is mechanical. The moon is 3.84 times 10 to the 8th meters from the Earth. So the distance from the Earth to the moon is 3.84, make sure I got, yes, times 10 to the 8th meters. How long would it take to travel that far? Well, you know that distance equals velocity times time. That's the simplest if you're going at a constant velocity. So the time is simply the distance divided by the speed. 3.84 times 10 to the 8th meters. 3.00 times 10 to the 6th meters per second. If you put that in a calculator, and it takes 1.28 seconds. That's amazingly fast. The last thing I want to talk about in this video is the different types of or classifications of electromagnetic radiation. And we need a mnemonic to remember this. And the one that I have always used is red Martians invented very unusual X games. And that's going to help us remember radio waves, microwaves, infrared radiation, visible light, UV radiation, X-rays, and gamma rays. All of those are different parts of this electromagnetic spectrum. We can start way down here with, let's make a graph of wavelengths. Remember that the symbol for wavelength is lambda. We measure the wavelength in meters. So if we start way down here at around 10 meters, some radio waves would be even longer than that, maybe 20 meters. And then 1 meter, 10 to the negative 1 meter. And then to save space, we're going to kind of jump a little bigger. 10 to the negative 5, 10 to the negative 7, 10 to the negative 9, 10 to the negative 11. So electromagnetic radiation can have wavelengths as long as 10 or 20 or 30 meters, or as small as 10 to the negative 13, really small. We classify electromagnetic radiation based on its wavelength or its frequency. These long waves down here are radio and television waves, and you know what those are. We've used those for broadcast for years. We can go up a little farther in this range, and I draw them overlapping because there's not a clear cutoff, with microwaves. Those are what we use to heat our food. It's also the type of electromagnetic radiation that is used by cell phone towers. Here we have infrared radiation. Infrared radiation is also what you think of as radiant heat. It's also the type of electromagnetic radiation used in your remote controls to turn your television on and off. And it's also used in, quote, your controlled cars, the little remote control cars. Those use infrared. Now, the tiniest little part is a little tiny sliver in here. There's a little bitty part of the electromagnetic spectrum that we call visible light. It goes from about 4 times 10 to the negative 7 to about 7 times 10 to the negative 7. So really small, it is the smallest part of the electromagnetic spectrum, but probably our very favorite. If we go a little higher, in here, this is our UV radiation or ultraviolet. We get most of our ultraviolet light. You think of that as being like a black light. It's also the type of radiation from the sun that causes sunburn. Most of the light that we get from the sun falls into this category right here. Infrared, visible light, UV. Fortunately, our atmosphere protects us from this high energy gamma rays and X-rays from outer space. We certainly don't want that. So our atmosphere is really important. If we go up a little higher, in here, these are X-rays. And we know what we use X-rays for, and if we go up even higher still, and on out, these are the highest energy rays. These are gamma rays. All of these that are higher than visible light are known carcinogens. Ultraviolet radiation causes skin cancer, X-rays can cause cancers and birth defects, and certainly gamma rays can cause a lot of cancers and possibly birth defects. So generally speaking, this high end is more dangerous. As you go from one end to the other, this end down here by radio, we're talking long wavelengths. We're talking low frequency and low energy. Energy is directly related to the frequency of light. As you move to the other side, over here, you get very short wavelengths. You get high frequency, high energy waves. Now, if we go just a little farther, we can take this little section that I called visible light and bring that down here. And we said that visible light goes anywhere from about 700 nanometers at the longest to about 400 nanometers at the shortest. This is red light, and this is violet. In between red and violet, we have orange, yellow, green, and blue. Human beings actually see best in this kind of yellow-green section. There are some other types of animals that can see higher frequencies than we do. They actually can see up into that UV range or possibly see lower frequencies down into the infrared range. But that's where humans see. When we think about color, color is related to the wavelength of light. It's impossible to be perfectly monochromatic, but monochromatic, we think of it being a single color of light. But what we really mean when we say that is that it's a very narrow band. For example, if you had light from 400 to 401 nanometers, you'd have one particular color of violet. If you had light from 430 to 431, you would have a somewhat different color of violet. But you could have violet light that had everything from 400 to 440. It'd still look violet. The light we get from the sun is white light. If you have all of the colors mixed together, they do make white light. We can use different types of filters and things. If you put a piece of red saran wrap or cellophane over your flashlight will make a red beam of light because that filter is going to absorb all of the colors except for red and only let that red light go through the filter. All right, I'm going to stop right there, but that's our introduction into electromagnetic waves.